Good morning. My name is Chantal Frisse and I'm giving a presentation on how to model a pavement design in Diana. Here you see a pavement with a pallet rack on it, and what I'm going to do is I pick out a part of it, so only the 4 legs of the pallet rack, and model the slab around it. All the edges I will clamp them. In this case I will not take into account the forklift truck on the model. If you want to do that as well, you need a bigger model, because then you have a loading in the easel as well. And now, due to only a part of your slab, you have all, because of the symmetry, then you have a lot of trucks. So if you want to model the truck as well, you need a bigger model that you can apply the distributed load of the truck as well. But in this case, this showing model, I only take out this part and model the load only of the legs of the pallet rack. If you open Diana, Diana looks like this. And first, to start with, to create a new model, I select a new project and I make a 3-dimensional model, and I want to use hexahedron elements and use quadratic elements to get a better stress and displacement fields. Now you see that we are in the geometry part, and here you have your graphical part. And first I need to set up the units, but during the modeling you can always change your units, but in this case I want to use millimeters and I want to use newtons, so the mass will be into tons. For the slab, I will create a sheet. Call it slab, and it will be the dimension that I just showed you in the slides. It is only the dimensions of a width of 2.8 meters. The height is 5.5 meters. And here you have the dimensions of your slab. I will do the same for the first leg of the rack. So I create a sheet, leg 1. And the dimensions of this base plate is 127 millimeters by 152 millimeters, but it should be positioned somewhere over here, and I will copy it to get the 4 legs. But the first one should start at 1.336.5 millimeter. The Y is 1424. So with the width of the 127, I will be at 1463.5, and then this is 1576, and this is then the original 336.5. And you see here is the position of the first leg. That looks okay. You see all the geometry that I've created is logged in this geometry tree. And everything what I've done until now is also logged in the command console. I will copy this leg to get the other legs. So I will select this leg. I will move it in Y direction over a distance of 1.1 meter. You can see where it is, looks okay. So this is the first rack, and the second rack I will copy both, and they will be copied also in the y direction of 1.4 meters. So you see now that there are two racks with the back to each other, and you see the four legs of the rack. I only created these sheets to apply distributed loads on this leg, and that's why I need the geometry for that I can make the imprints of this surface on the slab. So that is the next step. I will make an imprint on a face, taking the slab, and I take the four legs as an imprint. Now you see that you have one geometry left with an imprint of the four faces of the four legs. That is the geometry that I need. So the next step is to define the boundary conditions. So this slab will be on grade. So at the bottom there will be supports in all directions. So I create a boundary condition that's called bedding. It will be on faces. I select all faces, so the four legs and the surrounding of the slab itself, and I will support it in three directions. For the symmetry plane, on the edges on X direction, this will be the edges. So this line and this line, you can also click on it. This will be supported in X and rotated in Y. Okay, and we do the same for the symmetry planes in Y. This will be supported in Y and a rotation on X. And here you are, you have created all your boundary conditions. The next step is to apply the loads. So first I will define the self-weight. Okay. The next load case will be the uniform distributed loads. It will be on the faces, distributed loads, and it will be on all faces. And this I want to enter the values in meters and kilonewtons. So if I change it, you can see it directly is changing in the dialog as well. And I want to enter -100 kilonewton per square meters in Z direction. This is the uniform distributed loads, and we do the same for the distributed loads on the legs of the pallet rack. So I create another load. I will call it rack. This is on faces, distributed loads, and if you enter the values for this rack. It's depending on the force per length of the rack. This was given of 132 kilonewtons, and divided by the area of the leg, you will end up with a value of minus 6,838, and it should be applied only on the legs. So the 4 faces in vertical direction. So in your supports, of in your loading, we have here all the load cases, and if I view only the load of the rack, you can see I applied only on the area of the leg a distributed load. For the analysis, I also want to create a load combination. So I will also create an extra load combination where I apply the distributed loads in combination at the rack at the same time. That's all about the loading. So the next step is to attach the material behavior to your geometry. So I will go to select all the geometry, so it's complete slab. I will say it will be curved shell elements, and the material behavior will be a concrete and masonry model, and it will be based on a total strain based crack model. First you have to enter your linear properties, and now I'm going back to the newtons and millimeters. So the Young's modulus of C25 will be 20,884, a Poisson ratio of 0.2, and a density, if you prefer to have it in kilonewtons per cube, it will be the 2400. We will choose a rotating total strain model, and here we are going to use the behavior of when it reaches the tensile strength, it starts to crack and you need a softening model, and we are going to use this, the FIB fiber reinforced concrete model. So you have to define and enter the values of your stress as a function of your crack mouth opening. This is shown over here. You can do the bending test, and you get a curve and values how this stress is related to your crack mouth opening. And what we are going to do is we enter the values on specific points. We take out of the bending tests the FR1, the FR4, that is the maximum when it's reaching, and it is then 0 again, the stresses at a crack mouth opening of 6 millimeters. We are not depending on this graph how steep this line is dropping back to the stresses. This value could not be equal to the value out of your bending tests. If it's too drops very steep back and then returning, then taking the value out of the bending test is too large and you put too much energy in your model. Normally what we recommend is to don't model the peak at all or reduce the first value of your FR1, that you get the right energy in your model. In this case, I will not use the real tensile strength, but get more a plasticity model and start with the value of the FR1, keep it constant, and then a little bit of hardening and go back to 0. So now I will enter the values. Again in newtons and millimeters. In this case, this will be the tensile strength, the same as the first point. And this first point was reached at a crack mouth opening of 0.25. Then it's strengthened a little bit to 0.5 towards a crack mouth opening of 3.5, and the stress is back to 0 at 6 millimeters. Here you can apply a stress factor on this model that you have entered. So if you want to use your safety factors in the ultimate limit state, it is 1.5, but this is a multiplying factor, so we have to enter here the value of 1 divided by 1.5, so it will be 0.67. For the compression, we have to enter the behavior, and we take a parabolic curve, and we take a tensile strength of 33. The energy on fracture energy in compression is 0.38, and the residual compressive strength is very low. We take, for example, the 0.1 Newton per square millimeters. That is about the material behavior. For the geometry properties, we have to say what is the thickness of these shell elements. And in this case, the thickness is 200 millimeters. And we take a shape that it is just flat. Okay? And the last one is data. It is related to your integration scheme. In default, a regular curved shell element has only 3 integration points over the thickness of your element. If you're running a nonlinear calculation, you need more integration points over the thickness, so that's why we enter also a data ID for the slab, and we add later on some specific information about these number of integration points. Okay, so now you see that in the element data we have a slab, and for this one we add, as I just said, information about the number of integration points. So we add integration points, create numerical integration points with a value that is called a regular, and we have to enter the number of integration points, and that is done the number of, and this will be 5. I take now 5 integration points over the thickness of this slab. The next step is to model the grades underneath the slab. So we are going to create a model interface underneath. We will call it the bedding or the grade, and it will be on the faces, and we select all faces, and this will be a boundary interface because it's not in between 2 points of group of elements, but it's on the boundary. And we have to select a new material behavior for it. That will be the bedding. This will be interface elements. You can make also a nonlinear material behavior with a column friction and so on, but in this case, for the showing purpose, I only use a linear elasticity model for this bedding. So herefore we have to enter a normal stiffness and the 2 shear stiffnesses. In this case we have a normal stiffness of 0.87 and a shear stiffness is a tenth of the normal stiffness. Okay. We create also a bedding. The geometries of the bedding. And the data will also be bedding. And the support will be also the bedding. So now you see in the geometry that we also have bedding elements, so the grade under the slab. The last thing that we have to do is the meshing. So create the mesh. We can add some seedings that we want to have small elements around the legs and a little bit larger elements at the edges of your slab. We start with saying that all the elements of the slab will be with an element size of 250 millimeters. It will be hexa elements and linear interpolation. You can preview how these element sizes compare to your geometry, and this looks okay. So I say okay, but I want to have smaller elements at the location of the legs. So I select all the edges of the legs and give here an element size of 50 millimeters. So that's it. I will press the button Generate Mesh. And here you are. Here you see the mesh with small elements around the legs. Here you see the 4 legs locations and the little bit bigger elements at the edges of your slab. So now the mesh tab is filled. You see the slab, and you see also that there are interface elements at every location underneath the slab. Now your model is ready, so the next step is to go to the analysis. You have to set up an analysis. So in this case we add a nonlinear calculation. And we start with adding first the weight. I will call this weight. And we add load combination number 1, that was the weight load, and we apply it. A nonlinear calculation works incrementally, so the next execute block will add up the information and the load towards the last step. So I will create a new extra load steps, And so in this case I will add the uniform distributed loads and the rack in the combination of together. And we first go to the serviceability state level. So I call it SLS. And in this case I will need the load combination number 4. That was the combination of the distributed loads in combination with rack loads. And I will take small step 0.1 and that 10 times. So at the end I have a total of 1 on your construction. But we also want to go to the ultimate limit states, so I will add an extra load block where we go to the 1.2 multiplied by the weight. So we increase the weight a little bit more. Load combination 1, 2 steps of 0.1. And we add an extra block to get to the ultimate limit state, because we need to go to a factor of 1.5. We already have the 1, the SLS, so we need an extra of 0.5. So in this case I take 5 steps of each 0.1 on the loading factor of this rack and distributed loads. For the results, I want to specify some specific input, because we want to see what is the displacement, but also want to see what is the crack width of your model. And in this case, this is the strain, crack width, green, and in the principal direction. You can also add some stresses and strains and whatever, but I will focus on those two. Close, close. So that is the setting up of the nonlinear calculation. So the next step is to run the analysis. I will go to the message, run the calculation. And you can see that all the steps is incrementally increasing the loads, and see that everything is converged, so it will continue to the next step. And in total we have 18 steps, and then we are at the end. Step number 10. So everything is converged until the end. So now we are going to view the results. So now we go to the results tab, and we are going to view the vertical displacements. So that is the deflection. You don't see anything now because the slab and the interface is viewed, and the bottom of the interface is supported, so we will not deflect. So I will only view the slab. And you see that due to the self-weight, you have a very small deflection of minus 5.4 A-2 millimeters. But if you then increase the loads, so I add the distributed loads with a factor of 0.3 and increase to when this factor is 1 at this stage, you see that the maximum deflection is now minus 2.8 millimeter, and this is at the location of the serviceability state. We are going to look at the crack of these at this stage, what will be the crack opening, the crack width, and you see that at the bottom of your slab it is cracked, and the principal crack width has a maximum of 0.16 millimeters. This is at the location of layer 1, so the bottom integration points layer. So if we go to the next layer, so going up, you see that the crack mouth opening is increasing, but it is still cracked. So at 3, it is halfway of your slab thickness. It is still cracked, but almost getting to 0. And now you see at the bottom side, due to the clamping of the edges of the symmetry plane, at the top it is cracked at the edges. It is small, but it is there. But you can see that it is over here not cracked anymore. It is 0. So due to the rack, it will be cracked half through the slab, and at the top it is also cracked with minor crack width. We can even continue to look at the ultimate limit state. So we increase the loads and we go to the last step when we have a loading factor of 1.5, and you see that now the maximum crack width is 0.28 and the displacement is minus 4.25 millimeters. So you have to check if this is okay, yes or not, with the codes, and perhaps you want to change the material model with another dosage of your fibers. So what I'm going to do is I change the material model and rerun the calculation and see what is the differences. Everything what I've done until now is all logged in your command console, and this can be run with a Python script, all these commands, and you can run it. What I've done, I created a Python script, a run file, a log file, and that is what I'm going to run now to get all the material models in here with the dosage of the other fiber dosages. But now I need where they are. Dosages, no pick. So I ran, and you can see that it does it, all the dosages is there. So if I now go to the geometry and all the materials, I also have now the dosage of 4, 5, 6, 7, 8. All these materials are now imported in the model. So I can only choose another model and the material is already there. So I go to my geometry, I go to the slab, and I will not use now the slab material model anymore, but I select this slab that was related to a dosage of 3 kilonewton per cube meters, and now I select, for example, the 12 kilonewtons per square meters. I click OK. To get the assignment of the new material to the slab, I have to remesh the model. It's there, and then I can rerun the analysis. What you expect now, because to the larger dosage of fibers, the deflection and also the maximum crack width should be decreased. So the analysis setup is exactly the same if you want to model the truck in the ISL as well. You have to model also a sheet for the location of the track. you apply a force on that, and you can use this force also in your analysis. In the meantime, the analysis has been finished, so I go back to the results and I look to the vertical displacements. I will only show the slab. So now this is the serviceability state. It is now a minus 2.61 and a crack opening of 1.13. And if the behavior is exactly the same, but you see that it's less cracked than in the previous lower dosage of fibers. And if I increase it towards the ultimate limit state, you see that it is now a crack principal crack width of a maximum of 0.24, so it's a little bit lower than with this smaller dosage. And the displacement, it is also now a little bit lower. It was minus 4.25 and now it is minus 4. That was my presentation on designing the pavements. If there are any questions, please send me an email or call me or send an email to Tino Diana. Thank you.